if I'm adding 1 molar A and B together, and I pretty much know the reaction is going to go to the right until it reaches equilibrium, but it's much harder to predict what will the concentration of C be once I get there. It might seem like a pretty simple thing, but remember that all the time this is reacting, it's not just C that's changing, it's A, and it's B as well. And each of those concentrations go into the equilibrium constant expression. And just to remind you what this one looks like, remember we put products over reactants. These concentrations. Remember the brackets mean molarity. And then we use this exponent to get the coefficient to get our exponent. Okay, so even if we knew this number, we have to figure out how these all change, and these are related to each other. So to set up this problem, and basically we're going to look at how do you get between an equilibrium constant and equilibrium concentrations. Okay, and it's using a Rice table. It does take algebraic equations. Sometimes they're simple and sometimes they're not. It depends on what you're solving for and the system that you have. But this is a tool that we're going to be using throughout this lesson, just kind of in general, and then we'll also use it for solubility and also for weak acids. So it's I want to say it's kind of like you're learning the conversion factor at conversion factors. You're going to need this tool. So we call it a Rice table. The R is for reaction, and I wrote my reaction up there. And then next is initial, and in this problem I was given that I had 1 molar of A and B. And so I put 1 there, and I put a 0 here because I'm going to pretend like I have no product. These are like my initial. And like I said at the beginning, sometimes on these problems it makes it a lot easier if you think about the reaction as occurring very slowly. Like you have initial concentrations and then you're kind of watching it go to its equilibrium position, equilibrium concentrations. So that's what we're doing here. Here's our initial, and then when I say change, what I'm saying is I don't know how much of A is going to react, and so whatever that amount is, I'm going to call it X. So I'm going to say X of it reacts. And for the next one, for the change for B, well, if X of A reacts, then 2X of B reacts. And I get that from the coefficient. I can see that for every mole of A that reacts, 2 moles of B have to react. So that's where I got the 2. And it's negative because we know the reaction is going to go to the right. Okay, and then if 1X of A and 2X of B react, what do I get? I will get a change for C. I will get plus X here. Okay, so this row is by looking at the coefficients that are in our chemical equation. We always do minus for the reactants and plus for the product or products. Okay, and then this last one is where I basically am just adding, I'm basically adding these two to say what it is at equilibrium. So I'll say 1 minus X for A, 1 minus 2X for B, and just X for our product. And this is what we were wanting to get to. This is an algebraic expression that we can put together to relate these equilibrium concentrations to our equilibrium constant. In other words, I can plug these algebraic expressions into my main equation, and I'm going to do that on the next slide. Okay, and there are lots of different ways that this can work, or what information you might have, But let's just say, I mean, this is definitely a possibility, that you throw these together and you wait, and then just say that you can measure C. Maybe you can measure the concentration of C once it reaches equilibrium. Well, then you can use that to figure out the equilibrium constant for this reaction. And so that would be helpful. And then also you could use that to figure out the concentrations of A and B, which would be helpful as well. So let's look at how that would be done. So what this is if I discover that I'm basically getting my concentration of C, so basically this is X. This is my equilibrium concentration of C, what I said here. If I want to get the concentration of A at equilibrium, I'm going to use my expression for A. It is 1 minus X. Let me write that differently. And I'm going to that's the concentration. I'm kind of fudging and being silly with the sig figs because I just use 1 and 2 there, but let's focus on the algebra here. So for B, I'm using this, and I am just plugging in. I didn't show it on the last one. I am just plugging in 1 minus 2 times. So now I have equilibrium concentrations for A, B, and C. And so I can determine the equilibrium constant for this reaction. First, I come up with the expression. Expression is just this equation where I say products over reactants, going back to my reaction, C over A and B, but the B is squared because of that. So then I'll plug in my numbers. And I determined an equilibrium constant. So all I had to do was throw some A and B into my reaction, and after it comes to equilibrium, I measure the concentration of one substance, and I measured C, and from that I could use the algebraic expression to determine the other concentrations and my equilibrium constant.